Today's essential question is going to be on the concept of differentiation. And the way we're going to introduce differentiation and the idea of the derivative and taking the derivative and stuff like that is with the problem of trying to find the slope of tangent line. Remember, a tangent line is a point on your graph where the line only touches it exactly at one point. So if you can imagine, if I wanted you to find the slope, the exact slope at this point, A, well, you can actually kind of get a couple of clues about slope. First of all, if you were to draw a tangent line to that point, if you can imagine there is a tangent line right there, notice that that has a positive slope. So I know that whatever value it is, it's going to be a positive value at that particular point. Unfortunately, we don't know how to calculate the slope at a point because the only slope formula that we have is a formula which requires 2 points. If you remember, the slope between 2 points is this formula, y2 minus y1 over x2 minus x1. So, unfortunately, I don't have a method of finding the exact instantaneous rate of change or slope at that point, but I can approximate it by picking another point, then finding its slope. Now, notice if I were to draw a line connecting those, it would not be a tangent line, but it would be a secant line. And if you remember, this was the tangent line right here. So notice it is a positive also value, positive slope. So it'll be similar, but it's not exactly that slope at that point. So the question remains is how do you get a better approximation? Well, let's think about this for a second. If you have these 2 points, first of all, your first point is A, and so its y value would be f of A. And then if you have picked another point, let's say A plus H, so in other words, we're picking a distance H units away from A, so this point would be A plus H, so its y value would be f of A plus H. So the way that you could get a better approximation is just simply reduce the length of H, in other words, get closer to A, so just move your point a little bit closer, and then that would give you a better approximation. So you see that would be my secant line, and you can move it closer, and there's my secant line, move it closer, there's my secant line. But if you notice, as you're getting closer and closer to A, your secant line is approximately approaching the value of the tangent line. Well, what does that mean, getting closer and closer to? Well, that's the concept of limits that we've been talking about. So if I ask you the limit of this slope, so then how would you find the slope between the 2 points? Well, remember, it's y2 minus y1, so it would be f of A plus H minus f of A over A plus H minus A, right? Because x2 minus x1. And you clean this up a little bit so you could say the limit of f of A plus H minus f of A over the A's crossed out, so it's over H. And so what are you minimizing here? Well, you're minimizing the length of H, so you're trying to make H approach 0. Now, again, we don't want H to be 0 because the moment that H is 0, that means you're directly on top of this point. You don't have 2 points anymore. And again, you can't find the slope between the slope without having 2 points. So this is just a limiting difference quotient. Well, that, as you get closer and closer to A, where H is approaching 0, that is going to give you not just the slope of the secant line, but it's going to give you the slope of the tangent line at that point. And that is the concept of what we call a derivative. So the symbol, one of the symbols that we use for derivative is a little apostrophe there, so f derivative at A, so it's asking, so this is telling me the derivative of the function at A is equal to this expression right there. And just remember, the derivative is your slope. It's technically the slope of the tangent line, or in other words, the instantaneous rate of change. Now, again, you could use other letters besides A, like if you wanted to use the letter X, so you could say the derivative of X is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. A lot of different books use a lot of different symbols, but this is the one that I'm going to use on the next couple of slides. That is the definition of the derivative using the difference quotient and the limit. And just remember, the derivative is your slope, or rate, instantaneous rate of change. And so that's a very powerful tool to help us find instantaneous rates of change, instantaneous velocities, and any type of instantaneous moment in time. All right, so let's keep on going. And if you take a look at this next slide, it says find an equation of the tangent line to the graph of f of x equal to x squared at x is equal to 5. Well, we know that x squared is a quadratic and it has this shape right there. So if you can imagine going 5 units out, so like 0, 1, 2, 3, 4, 5. So it's talking about this point right there. It wants to know, well, what's the derivative? What's the instantaneous rate of change? What is the equation of the tangent line at that point? Well, again, in order to find the equation of a line, you need 2 things. You need to know a slope. You need to know its slope and its at a point. And well, we've got the point because we know that the point is at 5, and you can figure out what the y value is by plugging in 5 into the equation. So 5 squared is 25. So there's my point. The question, though, is what's the slope? Well, you can't find the slope, the instantaneous slope, just 1 point, using the old definitions that you learned in middle school. So instead, we're going to use this derivative definition, or we're going to take its derivative. We can already look, and we can tell that if you were to draw a tangent line at that point, you notice it's a positive slope. So I know my answer is going to be positive for the slope. How are we going to calculate that? Well, let's go back and pull out our formula. So the derivative at a point x is equal to f of x plus 8 minus f of x over h, and that is the limit. I should have put that in front. So it is the limit as h approaches 0. So let me put that right quick. So the derivative, my derivative is equal to the limit as h approaches 0 of this difference quotient. So we're going to do a little bit of algebra. So f of x plus h. Remember that I told you that f of x is x squared, so f of x plus h. Doing some substituting in, you would get x plus h squared minus f of x. Again, f of x is x squared over h. And so here's where I'm going to do a little bit of algebra. I'm going to FOIL this out in the numerator, so I don't want to lose this stuff also. So I'm going to put the limit as h approaches 0. If I FOIL this out, I'll get x squared plus 2xh plus h squared minus x squared over h. And then I'm going to clean this up slightly. I notice the x squareds cross out. That gives me the limit as h approaches 0 of 2xh plus h squared over h. Now, if you tried doing direct substitution and plug in 0, you would notice that you would get 0 over 0, which is indeterminate form. So you're probably thinking, well, so what does that mean? That doesn't help me any. Well, I'm going to do a little bit of algebra. I noticed in the numerator I have a GCF of h that I can factor out. So I'm going to say the limit as h approaches 0. Take out the h. That'll leave me 2x plus h over h. So then I can cross out those h's. I can divide by h and those cross out. So that leaves me with the limit as h approaches 0 of 2x plus h. And now I can do direct substitution, plug in 0 for h, not for x. You see it's h is approaching 0. Put that in, you get 2x plus 0, which is 2x. So my derivative is 2x for that function, and specifically at the point at 5. So my derivative at 5 would simply be 2 times 5, which is 10, which means the slope at that point is 10. And so I have my slope now. My slope is 10, and notice it's positive, which I already assumed it would be. my slope and my point. I can write this down. My equation would simply be y minus 25 equals 10 times x minus 5. And that would be the equation of the tangent line to the graph of f of x equals x squared at x is equal to 5. So definitely a lot of algebra that you're having to use to work this out. All right. It says compute f, the derivative of f at 3, where f of x is equal to x squared minus 8x. So again, find the derivative. That's what it wants you to find. So remember the definition. So the derivative is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. And so I can just simply substitute in what I need to, f of x plus h into the function. And so that would give me x plus h squared minus 8 times x plus h, then minus the function, so minus x squared minus 8x over h. And so then let me do a little bit of foiling and algebra to clean this up. So I'd get x squared plus 2xh plus h squared, and then distribute, I get negative 8x minus 8x, h. Distribute again, I get negative x squared plus 8x all over h. It looks like a lot of stuff, but let's clean it up a little bit. So let's see, the x squareds will cross out. I see that. The negative 8x and the plus 8x that'll cross out. But that leaves behind 2xh plus h squared minus 8h over h. Again, like before, I see I can factor out common factor in the numerator of h, and that'll leave behind 2x plus h minus 8 over h. And just like before, the h's will cross out, and that leaves behind the limit as h approaches 0 of 2x plus h minus 8. And now doing direct substitution and plug in 0 for h, I would get 2x plus 0 minus 8, which gives me just 2x minus 8. So the derivative of my function is 2x minus 8. And what that derivative is it's able to tell you what the slope is at any given point. So if I wanted to find out what the slope of the this function is at any point, I would just simply plug in that value for x, and it would give me the slope. So very powerful. I specifically want the value of the derivative at 3, so I simply plug in 3, and that would give me 6 minus 8. That would give me negative 2. So my derivative would be negative 2. So at x is equal to 3, my derivative is negative, which that gives me an idea that at 3, my graph is decreasing. My function is decreasing because it has a negative derivative, because it has a negative slope. Very nice. All right, keep on going. So sketch the graph of the function f of x equals 1 over x. I already have that for you here. So here is partial. It doesn't show the other part. Part of the graph of f of x equals to 1 over x. It says sketch the graph of the tangent line at x is equal to 2. Well, remember, the tangent line is your derivative. And so at 2, if you notice, here's 2. So if you were to plot that point right there, you can imagine drawing a tangent line that would look something like that. And so there's my graph of the tangent line. And what that is my derivative of my function at the point 2. That is my derivative. And I would know one thing right off the bat about this derivative. I know that it would be whatever it is, it will be a negative number because it's a negative slope. So I drew that picture right there. All right, moving on. It says find the derivative of f of x is equal to 9x minus 5. Now, before you start writing out that lengthy definition, you remember the derivative is equal to the limit as h approaches 0 of f of x plus 8 minus f of x over h. Before you start trying to write all that like I did, remember, what does derivative mean? That means the instantaneous rate of change, or the slope of the tangent line. Well, if you notice this function right here, this is a linear function, which means it has a constant rate of change. It has a slope that never changes. What is the slope of this line? Hopefully you recognize the slope of this line is 9. So my slope is 9, which means my derivative is 9 everywhere. I mean, if you were to graph that function, 9x minus 9, it has a y-intercept negative 5. So 1, 2, 3, 4, 5. It has a slope of 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9 over 1. It's simply a line. It's a line that's increasing consistently. And so the slope, no matter where you are on this function, is always 9. So in other words, the derivative, no matter where you are on that function, is always 9. So when it says find the derivative of the function at x is equal to 2 and x is 5, both of those answers would simply be 9. In fact, it doesn't matter where you are on this function, the derivative, since it's the slope, is always going to be 9. So that's just helping you remember about what does it mean to be a derivative. All right, so let's talk about differentiability and continuity, and we'll close out this lesson. It says a function is differentiable on the closed interval AB if it is differentiable on the open interval AB, and if the derivative on the left equals the derivative on the right at any given point on the interval AB. One very important concept to understand, if your function is differentiable at a point, then the function is also continuous at the point. Now, the converse of that is not true. Continuity does not imply differentiability. However, if your function is differentiable, then it is continuous. Case in point, look at this example right here. If you notice, I've got the function of the absolute value of x minus 2. Now, looking at it, it looks continuous, and it is. There's no holes, no gaps. It's definitely continuous. However, I will say that it's not differentiable specifically at x is equal to 2. It is not differentiable at x is equal to 2. The reason is because, think about what derivative means. It means the slope. Well, what's the derivative to the left of 2? Don't know exactly what the number is. Well, I mean, I guess I could. It's rise over run, so 1, 2, 1, 2. So the derivative here, the slope on the left side of 2 is negative 1. The slope on the right side of 2 is positive 1. So in other words, the derivative, the left is negative 1. The derivative on the right is positive 1. Well, again, in order for it to be differentiable, it's got to be the same derivative on either side of that point. And so this is not true at 2, so that's why this function is not differentiable at x is equal to 2. It's differentiable everywhere else, but not at 2. So again, just because a function is continuous doesn't mean it's differentiable. However, if it's differentiable, it's definitely continuous. All right, take a look at this last example. I've got the function x to the 1/3, and it looks continuous because it is continuous. There are no holes or gaps, but there is one place where it's not differentiable, and that is at the point x is equal to 0. It's not differentiable there. And again, it's all about derivatives. Because if you were to find the derivative on the left-hand side, first of all, let's just draw some tangent lines. So if you notice, there's a tangent line, there's a tangent line, there's a tangent line. They're all positive, but if you notice, they're all approaching vertical asymptote, which means the limit would be approaching a vertical asymptote, which means the limit would be equal to infinity. Remember, infinity, even though that's can be an answer, that's not an actual number. And so because on both sides, if you draw tangent lines on this side, as they are tangent, but eventually as you keep on drawing them, they will approach a vertical tangent line, and you can't find the slope of a vertical tangent line. That slope is undefined, and so therefore you can't find the derivative at that point. So what you need to be able to look out when you're taking derivatives is you can't take derivatives of functions at sharp turns or points where you might have vertical tangent lines for your slope. All right, well, that's it for today's lesson.